Hello, this video is about capillary exchange. Now, I've drawn on the board a schematic of a capillary. So if you imagine that the heart is up here and it's sending blood through arteries and then arterioles, and then that blood passes through a capillary and goes into venules and veins and back to the heart. That's what we're looking at here. We say that this is the proximal end of the capillary because it's closest to the beginning, and this is the distal end of the capillary because it's closest to the end of the capillary. Now, we know, and we will talk more about when we get to the respiratory system, that during the time that blood is passing through the capillary, there is gas exchange. But capillaries are also designed for fluid exchange, as we talked about with capillary structure in the previous video. And that's what we're going to discuss here, is the fluid movement. Now you'll notice that I have these strange purple tubes drawn here. These are called lymphatic vessels, and they're open-ended vessels that are constantly applying suction or low pressure to this space outside of the capillary beds. So it's pulling fluid from the interstitial space back through the lymphatic system through lymph nodes, and finally, after passing through the lymph nodes, that fluid goes back to the circulatory system back to the circulatory system through the subclavian vein. All right. So I mentioned also before that when we're talking about capillary exchange, we're talking about an exchange between the interstitial fluid and the plasma. So the interstitial fluid is outside of the capillary and the plasma is inside the capillary, and we're going to look at what happens to fluids as they move through. Now you'll notice that I've written some pressures and numbers in the proximal and the distal end of the capillary. This top one is hydrostatic pressure, which is an outward pressure. It is the pressure due to the volume of plasma inside the vessel pushing out against the capillary wall. We also have colloid-oncotic pressure, which is an osmotic or an attracting pressure. It's due to the solutes, especially albumin and sodium, pulling water into or attracting water into the plasma. You'll notice that these numbers, or at least the hydrostatic pressure number, changes as we move to the distal end of the capillary. But the colloid-oncotic pressure does not change, and that's because the things that cause the colloid or account for the colloid-oncotic pressure are not going to be leaving the capillary. All right, so let's look at this first set. In the proximal end of the capillary, we have a hydrostatic pressure of 30 that's pushing outwards, all right? So that's going to tend to make fluid move out of the capillary or out of the plasma into the interstitial space. The colloid-oncotic pressure is 28, but with an inward pressure or an inward attraction force. So if we look at these two, the outward pressure is greater than the inward pressure. So that we say that we have a net outward pressure. And net outward pressure means that there is going to be movement of fluid out of the vessel, out of the plasma, into the interstitial space. Whenever you have fluid that's leaving the capillary and moving to the interstitial space, we say that we are seeing filtration. All right. So there's filtration or a net outward pressure at the proximal end of the capillary. If we move to the distal end of the capillary, hydrostatic pressure is now 10 pushing outward. And the reason that it's lower is because of the fluid that has left the capillary starting at the proximal end. So we have filtration, and because we are losing that fluid, the hydrostatic pressure decreases towards the distal end of the capillary. The colloid-oncotic pressure is still 28 with an attractive force. So now when we look at these two numbers, the inward pressure is greater than the outward pressure. So we say we have a net inward pressure, and this results in reabsorption. Which means that fluid is going to tend to be attracted back into the plasma because of the colloid oncotic pressure. So what this means is that plasma that's coming through the capillary, some portion of it is going to leave and become part of the interstitial fluid, and some of that is going to be recovered at the distal end of the capillary before the blood continues on through the rest of its circulation pathway. Now, whatever it doesn't get reabsorbed is carried away by the lymphatic vessels, and that ensures that we are left with the same volume of interstitial fluid. Because if we aren't left with the same volume, then it can lead to edema, or it's the definition of edema. Okay, so this explains what's happening in the capillary, that there's a filtration or outward pressure at the beginning, and that there's an inward pressure or reabsorption towards the end. That means that fluid can come out into the interstitial fluid where it's accessible by cells, and then it's returned to the bloodstream, either by being reabsorbed or by being carried through the lymphatic vessels and returned to the circulatory system after passing through lymph nodes. Now, what happens when these are not balanced? We end up with something called edema. So I'm going to erase some of these words here. Right, so I'll leave the arrows because that's what's supposed to be happening. All right, so we've got fluid leaving at the proximal end, fluid being reabsorbed at the distal end, and some of the fluid being carried away by the lymphatic vessels. All right, so how does edema work? Edema is defined as an accumulation of fluid outside of the capillary beds. Now, there are a number of things that can cause this. Anything that increases hydrostatic pressure, so if you have hypertension, that's going to increase the amount of fluid that leaves at the proximal end. And since the lymphatic vessels can't necessarily take away the excess fluid, and since the colloid oncotic pressure is the same and can only attract the same amount of fluid back, increased hydrostatic pressure is going to result in more fluid staying in the interstitial space. Another thing that can cause problems or cause edema is if you have a decrease in the colloid oncotic pressure. This happens when you lack dietary proteins. We discussed we haven't discussed it yet because it's in the blood video, but something called kwashiorkor, where children have a protein deficiency, and because of the protein deficiency, they aren't able to manufacture albumin. And without adequate albumin in the capillaries, there's no way to attract all of the fluid back into the capillaries, and it stays out here. So when you have decreased colloid oncotic pressure, you have less ability to reabsorb the fluid that has been filtered outside of the capillary. Another reason why you might develop edema is if there is some kind of blockage in the lymphatic vessels. All right, so I'm going to put a blockage here. Let's say there's a tumor somewhere that's pressing on those lymphatic vessels. If the lymphatic vessels can't pull away or siphon off some of the extra fluid here, all right, so it's not getting pulled away, then that means that there's going to be more fluid accumulating in the interstitial space, which is leading to edema. Now, edema is bad for you. It's not just how it looks, that it's puffy and swollen, but it also means that there's fluid that is not being circulated through the system. It can actually reduce the blood volume and lead to circulatory shock. but it definitely interferes with gas exchange. So if there are cells out here that are usually very close to the capillary, as fluid accumulates in the interstitial space, there is more space or a greater distance between the capillary and the cells that are exchanging with it. So exchange isn't as good too, and that can lead to tissue death, which is called necrosis. So edema, not good for you. Happens because there's a shift in the balance or a lack of balance between these three pressures. The hydrostatic pressure in the capillary, the colloid-oncotic pressure in the capillary, and lymphatic pressure or lymphatic suction.